up until this point, you've only been working with an equation, maybe of a line, maybe just using regular algebra with it. But now we have a system of equations. That sounds very daunting and overwhelming and official and robust. But it's not. A system of equation is one scenario that involves multiple equations at the same time. The goal of solving a system of linear equations, we're still working with linear, it's still the easiest function to work with, is to find where those lines cross, where that intersection point is. There are several different ways to solve a system, and it's best to be fluent in all of them because they each have their own place. Here is where your basic algebra skills are finally going to be applied. Solving a system by graphing. It's kind of a joke. So you graph the lines, which you know how to do, then you just look at it. Most of the time when you're asked to solve a system this way, the coordinate point is visually obvious, but it's not an effective way to solve any system of equations. Solving a system algebraically. Usually when you're looking at two different equations for lines, you need to differentiate or find some way to keep their values separate. And we use subscripts to accomplish this, which we've done before with like the slope formula. What's fantastic about the system of equations is even though we're looking at two different lines, we're only worried when the lines cross each other at one coordinate point. What this means is, by definition, the values for x and y are going to be the same in both equations. Since we can assume this, we can go into a linear system with an unknown xy and then kind of solve back and forth because we're only interested in when the values are the same. So no subscripts are going to be needed here. Solving a system of equations by substitution. This method is the best if one or more of your equations is in slope-intercept form, or algebraically solved for one of your variables. Remember that I've been drilling in your head to use parentheses when we do any sort of substitution. This is where it pays off. This 5 wants to multiply the entire value of the y, which in this case is a binomial already in simplest terms. This is where we absolutely must distribute that 5 across to get the correct answer. Solving a system by combination. This method is best if all of the equations are in standard form. Remember the addition and property of equality, how I can add the same thing to both sides of an equation and it maintains the equality? I'm going to apply that here. I'm going to add 1 to both sides of this equation. Over here, well, whatever I did to that side, I got to do this side. But I'm going to add specifically what 1 is equal to within this system. I mean, that this 5 is positive, so I'm just going to add that. So remember, the x's and y's are the same in both of these equations. We're only interested in the intersection point. So now I'm going to combine like terms. So 7x plus 5x is 12x. Negative 4y plus 4y. Oh, the y's cancel. Interesting. Okay, divide both sides by 12. And we have an x equals 1. Remember, we're trying to find the entire intersection point, but I only have one of the coordinate values. Well, just plug that x back into one of your original equations. It'll give you the y value. That's basic at that point. So we have 5. Maybe I can put it under here for consistency's sake. Subtract 5 on both sides. 4y equals 6. 4 on both sides. We have y equals 3 halves. So our full coordinate point intersection is 1, 3 halves. Yeah, that works. Cool. That was kind of an easy setup. We just did the combination and one of the variable terms just canceled out immediately. Well, sometimes it's not going to work that easy. We'll use the multiplication property of equality, potentially on both of them, to get one of the variable's coefficients to match. Once we've found the LCM, remember that one? Then it's the exact same method.